Hello class. I'm going to use this YouTube to provide you a little tutorial. I'll provide you little hints on the last question, problem 5 of assignment number 1. Okay, so hopefully this will help. So let's take a look at this question here. The question is, you basically have two gears. Okay, so the force is the gear acting by the other driven gear at here. Okay, the angle here is later when we learn this is called the pressure angle. Okay, there's a small gear which is basically the transmitting the torque to drive something else outside here. What you should notice is the bearing is between the gear at here. Okay, and there's another bearing here, so it's a little bit different from the general structure. There's an overhang here for this gear. Okay, for this question, the number one step, what you need to do is you need to come up with a free body diagram, basically. Okay, analyze this system, and bear in mind that we're dealing with equilibrium equilibrium system. Okay, so all the torque or force or moment, they should be in equilibrium. Okay, so let's take a look at this force here. Now, when you look at this force is acting basically acting on the gear with an angle of 20 degrees. Okay, and this force is in the ZY plane and here. Okay, so this force in ZY plane. So you can basically decompose this force, right, into two components, right? One is called, let's see, FA tangent, and the other one you can call it FA not tangent, and FA, let's see, R direction or axial direction. Okay, the axial direction. So this force in axial direction is basically it will go through the center of the gear. Okay, so similar for this force too, right? So you will go through this. So the this one you would call it FCT, and this one you would call it FCR, like this. Okay, yeah. Now, what will be the force that could generate a torque, or what will be the force that could be generate rotation, about this shaft of the gear? Apparently, it's this tangent force, right? It's tangent force here. The question gives you the force FA, so apparently the FAT, right? You can calculate the FAT, which is FA, right? Cosine 20 degree. Okay, FA is 300. Okay, so you can calculate that. Okay, FAR you can also calculate, which is FA sine 20 degree. Okay, so now you have the two components of this force here. Okay, with the calculated force FAT, the tangent force FAT, we can calculate the torque, right, generated by the FAT, which is FAT times, right, the distance or the radius of the gear. Okay, and radius of the gear, which is half its diameter, and I think the value of the radius gear is giving us what's the radius is giving us 24/2, right? So FAT. So you can calculate the torque. Okay, and the direction, what's the direction of the torque, right? The direction of the torque, use your right hand rule. Okay, your R here, so R cross F. Okay, R cross F. This is actually it's this way here, right? It's driving it this way. Okay, so that's the torque generated by this force over here. Okay, now the system is in equilibrium, then you will have a torque, right, from this direction due to the force over here. So that's why you can keep it as balance, right? So let's go back to this gear at here, right? It's gear. Let's see what do we have over here. Okay, what do we have? So for this gear, right, what's the tangential force? Tangential force is FCT, right? It's FCT equal to the FC cosine 20 degrees. Okay, and the torque, right, generated by the FCT, right, will be the same torque as the torque over here. So T, this T here, will be equal to FCT multiplied by the half diameter of this one here, right? Yeah. So the half diameter of this small one, see, is 10 inch. So that's 5 inch right here. Okay. So this one equal to this. Okay. Now you can solve. Now you can solve for FCT. Right? FCT will be FAT 24/2 divided by 5. Okay. And once you solved FCT, and you can go back here, right? You can solve for FC. Okay. And once you solve FC, you can get FCR. Okay. Yeah. So now you have all the force components, okay, because of these two forces here. Okay, now you're ready to draw a free body diagram. Okay, and now you should realize that in this case, what you have is a two-plane bending, right? One plane is the XY plane. Okay, so if I look at XY plane, let's say suppose that this is my shaft. Okay. This is my shaft. So XY, this is x-axis, okay, and this is y-axis. Let's see, right? Yeah. This is the beginning of the shaft over here, or the location of the bearing. Okay, and this is the A point, which is the gear location, and this is a B point, which is the location of the other bearing, and this is the C location, which is the small gear location. Okay, so at the two bearing, okay, at the two bearing location, okay, you will have a certain kind of a supporting force. Okay, let's say you call that ROY and RBY. Okay, at location A, right, you have the force coming out of the force on the gear. Okay, and what will be this force? Should that be FAT or should that be FAR? Now, because in the XY plane, so this actually should be the FAT, right? FAT, and the direction of AT, okay, is in the positive direction of the y-axis. Okay. Now these two ROY or BY, we don't know which direction it points to yet. So at the beginning, I can simply use the direction points up. After you calculate if the value of the force is in the opposite direction, then you change that. So our C at C location, right? You have the FCR at here. Okay, you have the FCR actually. Okay, so now you know this too, and you can use equilibrium equation to calculate, okay, the ROY and RBY. Okay. Now, when you calculate the ROY is actually negative. This you should get this, and RBY. Okay, now this is positive, so the direction the same as the direction that as we assumed, 158.1. So now this is our XY plane. Okay, XY. So you get this one here now. Okay. Yeah. So the bending moment in this plane, right? You care about the bending moment. The bending moment in this plane can be easily drawn now. Okay. So if this is the shaft, okay. Now bending moment, one of the tip is always 0 at the two ends. Now the two ends doesn't mean it's the two ends of where the bearing is. It's actually it means the two ends of the force. Okay, the force is, see, this is a bearing location, but this is a force location, the small gear, the gear C. Okay, but the bending moment will be 0 over here, and it will be 0 over here. Okay, so you can calculate the bending moment. Okay, in this particular case, if you don't like to calculate bending moment, okay, but you know, let's do that. If I calculate the bending moment, and what I get is the bending moment will have a turning point either at A location and at the B location. Okay, so R01, the actual is this way here. Okay, if I calculate that, and what would that be? And chances are it'll be something like that. Okay, and it'll be something like that. Okay, right? So so details of the bending moment you can so there should be a turning point here. Okay, not a straight connection. Okay, so because A here. Okay, but there's a taper here. When you have a two-plane bending, okay, in most cases, okay, or maybe in all cases, the two critical locations that are of particular interest to you is always the two locations, you know, the two locations in between these two ending forces. Okay, so it's going to be either A location or B location that's going to be particular interest to you. Okay, now let's take a look at the free body diagram for the other plane. Okay, so for the other plane, okay, it's going to be in the XZ plane. Now if you look at that, actually the Z is not pointing up here, the Z is actually pointing down. Okay, so this is in XZ plane. So suppose that your shaft is over here, right? So let's say O, A, B, C. Okay, then at A location, okay, you will have your FAR. Okay, at C location, you will have your FCT. Okay, FCT. Okay, now at O and B location, you will have your bearing supporting force. Okay. Okay. So we don't know the direction again, you just assume a direction in the beginning, and then you can calculate the user equilibrium equation for these two. Okay. So you should get ROZ, okay, equal to the negative of this. Yeah, sorry. Yeah, so if this is the direction here, your ROZ is going to be positive. Okay, so basically the ROZ will go this way. Okay, and RBZ is the same direction as indicated like that. Okay, so RBZ is this direction. Okay, so now you get these two, and you can draw the bending moment diagram. But as I said, okay, in this case here, if you don't want to draw a bending diagram, that's fine actually, because your location of particular interest is going to be either at the A location or at the B location. Okay, so A, B, okay, are the critical location, but there has to be one that is more critical than the other. Okay. Then how do I know that? Right, we essentially will have to calculate the this is two plane bending. We have to calculate the overall bending from the two planes, right? So in the XY plane, right, in the XY plane, okay, in the XY plane, then what will be the bending moment at A location will be bending moment at B location, and in the XZ plane, what will be the bending moment at A will be bending moment at B, right? So in XY plane, okay, in XY plane, what you can do is you without the bending moment diagram, you can still calculate. You know, remember as in the class I mentioned, if I want to know the bending moment at the A location, right, and all I need to do, you know, basically MA, okay, at here, this is going to be in the Z direction, right? So MZ is going to be just the supporting force is ROY multiplied by the distance OA. Okay, that's your MAZ. And MBZ, okay, essentially you can simply use FCR multiplied by the distance BC. Okay, so that's going to be your bending moment in this plane. Okay, and in this plane here, you're in the XZ plane. Okay, your M, now this is going to be in the Y direction, so MAY. Okay, this is going to be just ROZ multiplied by OA, and MBY is going to just be this FCT multiplied by BC distance, right? Okay, so now you have two plane moment, and what you need to do is compare, right? So the total bending moment at A location is simply MAY squared plus MAZ squared, right? And MB equal to MBY squared plus MBZ squared. Okay, so you need to compare these two. Okay, see which one is bigger. Okay, see which one is bigger. Okay, so you choose the bigger one as your critical location, right? And that's where you have your maximum bending moment, right, at each one location. And then you analyze the shear stress tau at that location, right, due to the torque, right? Then you use the stress element, calculate maximum principal stress, and things like that. And then you come back to torque, right? So apparently you will have zero torque between O and A, okay, and between A and C, okay, the torque is T, okay, the torque is T, okay, and you will have shear stress within this location here on the cross section of the shaft. So that's the hints about this question, and if you follow this, I think you should be okay. Okay, so let me know if you have any more questions. Okay, and hopefully this helps. Okay, thank you.